Fine. Let's revise quickly before we proceed with the next subtopics in the chapters. Priya,
Yes, ma'am.
can you just tell what is elimination?
Ma'am, elimination is defined as excretion plus metabolism.
You can avoid using the word plus. I would have used that word to make you understand. It's a combination of excretion and metabolism. Navya,
Yes, ma'am.
what is disposition?
Drug disposition is the combination of distribution and elimination.
Fine. Vandana, Midun,
Yes, ma'am.
okay. Which route of administration you feel absorption is a preliminary step?
Oral route.
Fine. Any other route can you guess other than the oral route, where absorption will be the primary step? You just recollect. You can't say don't know. You are in fourth year pharmacy, dear. Okay, it's not a tough question I asked you. It's very simple. You just give me the route of
for every route, absorption is needed, ma'am.
every route absorption is needed. Lipika,
And still, I
1 second. Lipika,
Maybe topical.
no, he said every route requires absorption. Do you agree with that statement?
Because the drug has to enter the systemic circulation, absorption is
No. You just answer yes or no. You agree with the statement of Midun stating that every route of administration, whichever route you administer, absorption is default.
Ma'am, no, ma'am.
Who is this?
Terminal and all, we need absorption.
Which one?
Oral and all, we need absorption, ma'am. For parental routes and
parental means which other routes you feel? Sanskriti?
Yes, ma'am.
Now what you feel? Does every route of administration, there is a step, absorption step involved?
No, ma'am.
Can you tell example?
Ma'am, in case of sublingual, there is faster absorption.
I'm asking you very simple, straightforward question to all of you. Understand what I'm asking. I am asking you, any route of administration, absorption, do you feel that absorption is the primary step? That is the first step which happens for any drug through any route of administration. I'll give you an example. Transdermal,
Absorption is necessary.
sublingual,
Absorption is necessary.
then rectal.
Absorption.
Fine. Siddharth.
Yes, ma'am.
What is the opinion about IV route?
Ma'am, for IV also, absorption is required.
Please think and answer. What is IV? Full form.
Intravenous.
Intravenous means?
We are directly injecting into the bloodstream.
Then, do you think that absorption is there? No, come
No,
on.
ma'am.
Then,
No.
mute yourself. Samarth?
Yes, ma'am.
Which Samarth is this? I know you, or you know me?
Yes, ma'am, you know me. I know you too.
Fine. No, I'm not able to recollect. Samarth. Yeah, I remember. Anyway, Samar, you agree
Yes,
with
ma'am.
that IV route doesn't require absorption?
Yes, ma'am. It doesn't require.
Yes, please remember, mute yourself. Remember all of
Okay.
you, okay? Almost all the route of administration except IV route, absorption is the primary step. Please remember and keep this in your mind. You are in Form D very much oriented towards the clinical applications. So your knowledge about all this should be 100% correct. So any route of administration other than IV, it will be, the absorption will be the first step which happens to any drug. IV doesn't happen as it's that told the answer. The drug is directly administered to the systemic circulation. So you're bypassing. The drug is not necessary for a drug to undergo absorption. From capillary, it will circulate throughout the body. You couldn't call that as an absorption. That's called distribution. Fine. So in continuation, yesterday we learned what is absorption definition. We understood movement of unchanged drug from the site of administration to the site of measurement, that is your plasma. That is a plasma sample. Also, we got some idea about the mechanism, the major mechanism by which the drug undergoes absorption, transcellular and the aerocellular. To justify the transcellular, two theories were proposed. That's what we learned yesterday. Lipid bilayer theory and the fluid mosaic. And lipid bilayer, based on the structure of the plasma membrane, it justifies the movement of the lipophilic drug molecule only. It didn't had answer. In that theory, they didn't had any justification to say the movement, to prove the movement of the hydrophilic molecules. And the other theory proposed was the fluid mosaic model. According to this model, the hydrophilic molecules, which even they are charged and smaller in size, can easily pass through the membrane because of the presence of the protein channels, which are buried inside the cell membrane. Okay, fine. So this is what we just understood about the theory behind. Now so this slide I just added up to tell you that there are different functions a protein can exhibit. The proteins which are present in the plasma membrane plays different roles. So right now, with respect to the absorption process, we are imagining protein is functioning as a transport channels. Means a gap, passage which allows the drug molecule to move. Not only that, it can act like a receptor. We know that proteins in different parts of the body and even in the cell membrane, it can act like a receptor. Which part, let us not worry. It can act as a receptor, it can act like a carrier. That is a transport carrier. So it plays more than one function. Different proteins have different functions depending on where it is situated in our body. So it plays multiple roles. I'm not telling that single protein can play multiple roles, but different proteins play different roles. Not necessarily, again, the same protein will have the different functions. So depending on where the protein is situated, it starts playing different roles. So if you just look at this diagram, just to make you understand the movement of the molecules through our plasma membrane. And now we are talking plasma membrane with respect to the GI membrane. That is the epithelial cells. That's what yesterday in the class I told you. We have epithelial cells in the GIT. The epithelial cells which are present in the GIT is nothing but a normal cell which will definitely have a plasma membrane. Now, with respect to this, we are understanding how the movement of the drug molecule can take place. So look at that first one. It's a carbon dioxide and oxygen. That is a gaseous molecule. It doesn't create much problem for us because they are gaseous in nature and it can just permeate through the GI membrane. That is the epithelial cells. Coming to the next one, benzene, which is hydrophobic in nature. These are only the example to make you understand how the transport happens with respect to the physical chemical property of the molecules. That is drug molecules in our case. So benzene, if you look at it, is hydrophobic in nature, and we know that phospholipid bilayer structure is phospholipid bilayer structure, and it is highly permeable to the lipoidal substance, that is substances. So benzene is hydrophobic, nothing but lipoidal in nature, so it can easily pass through. So coming to the next one, small polar molecules doesn't have any difficulties because they are smaller in structure, and because of the smaller, it can easily pass through the channels which are created by the proteins. The problems start persisting for those molecules which are polar and larger in size, and also those molecules which are small, actually even charged. Thus, it is smaller in size, but they are charged. So, major problem with respect to the initial knowledge of the cell membrane, the problem exists for the large polar molecules and for those molecules which are charged. So, with respect to that unit membrane theory or the lipid bilayer theory, whatever we just studied, no? So according to that theory, the first three molecules doesn't have any issues for passing through the plasma membrane, but the next two has the problem. Okay. So with respect to this, there are three properties we can conclude that the permeation of any molecule depends on the three properties, that is polarity of the molecule, charge of the molecule, and the size of the molecule. So, the three characteristics of a molecule that determine the permeability of the membrane are polarity, charge, and the size. So, at this point of time, we might feel that, okay, there are many molecules which cannot pass through our membrane. That is not the case. In reality, there are different mechanisms by which even this larger polar molecules or even this charged molecule can easily pass through the membrane. That's what we are going to learn. That is the carrier systems. So there are different mechanisms other than your normal based on hydrophilic and lipophilic property. There are even other different mechanisms by which even the drug try to cross the plasma membrane barrier of the epithelial cell with respect to GI tract. So coming to now in detail. So this is what one of the question you can expect. Sorry, at this point I don't know, but as based on the my teaching experience, I am expecting this is one of the important discussion which you can expect in the exam. That is as for the major question, 10 marks. So mechanism of the drug absorption, whatever we learned is the transcellular and the paracellular. That is a broad way of classifying. Now in detail we are going the mechanism of drug absorption. I expect you to note down this mechanism. Fine. So passive diffusion, the first one. The second one is the pore transport. As I said, I'm expecting you to write. So hope you are all writing the same points, whatever I'm stressing upon. So second one is the pore transport. Third category is the carrier mediated transport, which is further classified into this. Under the carrier, you can subdivide into facilitated diffusion and the active transport. Okay. The next one is ionic or electrochemical diffusion. So remember, this facilitated and the active comes under the common third category, that is a carrier mediated. The fourth is ionic or electrochemical diffusion method. Next is ion pair transport, and the last one is endocytosis. Means there are different mechanisms by which you can expect a molecule can absorb or transport across the membrane. And since we are talking about the oral route, this is the mechanism of drug absorption through GI tract. The question can be like this: explain in detail mechanism of drug absorption through GI membrane. So it's wherever the absorption is happening, the mechanism remains same. This is a broad classification which you can apply for any part of our body. But for your syllabus, it is a mechanism of drug absorption across the GI membrane. Fine. Hope everyone have written this. I'll proceed further. Now let's learn the first one. that is passive diffusion. Look at the diagram carefully and analyze. You will understand the pictorial representation is always gives us a better idea. So if you just look at the diagram, what you feel, you can see the bilayer structure, right? Plasma membrane bilayer structure is visible. Okay, also you can see one protein which is acting like a channel, and the membrane outside, that is either side of this, one is the GI lumen and other one is the this one. I'm talking about this part. The one part is the inside the cell, that is your cytoplasmic membrane, that is the that is cell cytoplasma, which is the inside the cell, and this is the GI. Okay, the drug. So with this schematic picture, what you can understand is the drug is the molecules are trying to cross the plasma membrane, and it is depending on the polarity. That's what we understood in the previous slide. That is the three major characteristics which actually plays in the movement of the drug molecules: polarity, charge, and the size. All this property will start influencing the movement of the drug molecule. So now, when you say the word passive, we know that passive is energy independent process. Energy is not involved in this process. So it's an energy. The first important feature of the passive process is it's an energy independent process, and the molecules move across the membrane by a process called as diffusion. See, these are the different names you can expect, like absorption, transport, diffusion. It's all like they're related to each other. Absorption is a process overall. How the absorption is happening? By diffusion. This time the molecule is trying to diffuse across the plasma membrane. That's why it is called as diffusion process. So no need to get confused. It's the one and the same. We are learning about absorption only. And now in the passive absorption process, the absorption is happening by the energy independent process, and that process is also called as a diffusion process or diffusion mechanism. So what is that force which is driving the molecule? I told you in this diagram, there is the cytoplasmic membrane sitting here that is covered, that is inside the cell. The other one is the GI lumen. The drug is, tablet is disintegrated, drug is undergone dissolution. Now the drug is released inside the lumen. It will start moving inside the epithelial cell of the GIT tract. And to that happen, the driving force is the concentration gradient. The driving force is what? Concentration gradient. Means it's the difference between the concentration across the membrane. The difference between the concentration of the drug molecule across the membrane, that is concentration in the GI fluid and the concentration in the cytoplasma. So it is always the from higher to lower side, the driving force. So more the concentration gradient, that means more the difference between the concentration between this region, you can expect the faster will be the absorption happening. So the driving second important feature in the passive diffusion is the diffusion happens because of the driving force, which is the concentration difference or the gradient. The gradient word is best term to use at this point instead of telling concentration difference. Gradient and difference both are same, but it sounds good, gradient, when you use the word in the answer. So now, as I said, it is a difference in the drug concentration on either side of the membrane. Most of the drug molecules follow this mechanism, that is by the passive diffusion, which is an energy independent process where ATP molecules are not involved, and the driving force is the concentration gradient, and this concentration gradient is the difference between the concentration of the drug on either side of the plasma membrane. I know you would have learned all this in another subject, pharmacology. I don't know how depth or it might be repetition, but it's good one way. If you feel it's repetition, it's good. So now, as I said, it's a diffusion mechanism which is happening. Passive diffusion, energy dependent. The drug molecules are moving across the membrane by the diffusion process. And now this diffusion process is explained by the law called as Fick's-First law. Fick's-First law mainly talks, there are two laws which is governed by the fixed law. One is the first law and the second law. It is totally a different aspect. Anyway, it's not very important. But for the passive diffusion, to understand the theory behind the passive diffusion, it is explained by a law called as the fixed first law. So which states that, see, you might feel difficult to behind this definition of the fixed first law, but if you can remember this equation, it becomes easy for you to define the fixed first law. Simple. So whenever we write this equation, maybe some alignment problem is there, it is dq by dt. The dt has shifted, maybe the change in the computer. I have shifted from mobile to computer, so there's a change in the alignment. So DAK, oil in water coefficient, divided by H. H should come below this line, okay? Minus overall, minus concentration gradient, that is CGIT minus Cp. Please write down this equation dq by dt. So this is the differential equation which tells about change in a parameter with respect to time. That's called as a differential equation. Differential equation usually talks about change happening with respect to another variable. So in our case, the change happening here is the diffusion. It's happening with respect to time. So rate of change of diffusion with respect to time is given by D into A into K, that is oil in water coefficient. So D is the diffusion coefficient of the drug molecule, which is an inbuilt property of the drug molecule. Okay, and A is the surface area where exactly the diffusion is happening, and K, or that is oil in water coefficient. K is called oil in water coefficient, which gives us idea about the hydrophilicity and the lipophilicity of the drug molecule, and H is the membrane thickness. So now with this understanding, and the next one is CGIT, I told you it is the GI concentration and the plasma concentration. Difference in the drug concentration in the GIT and the drug concentration in plasma. Directly we are using the plasma concentration. I am not telling cytoplasmic concentration, because ultimately the drug which is released in the GIT is moving to the systemic circulation. While moving to the systemic circulation, I know actually it crosses many barriers. Let us imagine the first barrier is the GIT barrier, that is epithelial cell. Okay, it comes out of the GI tract. Then is an interstitial space between the capillary, that is your blood capillary, and the GI. There is a space called as interstitial space. Again, it enters through the capillary membrane and then comes to the blood. So all that in between transport we are just not considering. Overall, it is the difference between the concentration in the GIT and the concentration in the plasma, because plasma is the measurable point for us. So that's why we are trying to consider that concentration. So ultimately, it's the driving force. Though in the picture I told here, that is a concentration gradient is the difference between the concentration in the cytoplasma and the GI. It's nothing but, now imagine, now it has crossed all this and come out to the systemic circulation. It's the same, the concentration in the GI minus the concentration in the plasma, somewhere it comes here. So now let us look into the definition. So according to fixed law, it states that the drug molecule diffuses from a region of higher concentration to one of lower concentration until equilibrium is attained. And the rate of diffusion is directly proportional to the concentration gradient across the membrane. So whatever parameter you have written in the numerator is always directly proportional, and any parameter written at the denominator is always indirectly proportional. So it is directly proportional to what? The major parameter is the concentration gradient, and also directly proportional to the area, also directly proportional to the partition coefficient, and indirectly proportional to the thickness, that is membrane thickness. Okay, so the passive diffusion of a drug molecule across the GI membrane is explained by a law called as fixed first law of diffusion. So according to this fixed law of diffusion, the drug molecule diffuses from a region of higher concentration to the lower concentration till equilibrium persists, attained. And the rate of diffusion is directly proportional to the concentration gradient. Okay. Fine. So this is what the law which governs the or explains the passive diffusion across the GI membrane. So now just to understand what happens to the drug molecule when it is start getting diffused. The membrane is lipoidal in nature. We know that already. The drugs undergo partition process. Definitely partitioning is what? You know what is K, that is oil in water coefficient value? Means whenever you distribute the drug in the mixture of oil and the water, how much drug enters into the aqueous phase and how much drug enters into the that is the organic phase. So that gives us idea about the lipophilicity of any drug molecules. Okay, so this membrane, which is lipoidal in nature, the drug undergo partition. All the drug will not just enter directly. Depending on the lipophilicity and hydrophilicity, it start undergoing the partitioning. So aqueous GI fluid into the membrane. Okay, after diffusion to the membrane, they partition from membrane into the aqueous blood, and this is what every step throughout its journey, the partition goes on. Means it will start moving from the GA lumen till the target site by a process called as partitioning. So based on the hydrophilicity and lipophilicity property of the drug molecule, at every step, the partitioning keeps happening. And depending on that, the drug molecule keeps moving from one place to another place. So drugs that are more lipid soluble, which is more lipid soluble, have a larger value of K. Remember, that means there is a relationship between the lipophilicity and that's what I told you, oil in water coefficient value of it, and it's an inherent property. Means it is a property of a drug molecule. We are not going to add up this to the drug molecule. It is inbuilt property of the one of the physical property of the drug molecule. So greater the K value, that is oil in water coefficient value, greater will be the lipid soluble. Okay, so greater the K value, greater will be the lipophilicity. So greater the lipophilicity, more will be the permeation, because plasma membrane, across the plasma membrane, more lipid soluble drug molecule as comfortably permeate or absorb compared to that of the hydrophilic molecule. So greater the K, greater the lipid solubility, greater the diffusion. That means other way, more will be the absorption. So coming to this DAK, these are all constant. I told you D is the diffusion coefficient, which is the property of the drug again. Okay, and that cannot be altered. Every molecule have its own diffusion with respect to time. It's nothing but centimeter square per second. This much drug only can diffuse across the this area in this particular time interval, that is fixed. Okay, same the surface area, if you think it is constant. So we are trying to imagine that the D is constant, it's a property of the drug. A is also, can let us imagine constant, that is the area where it is actually undergoing the diffusion process, that is your GI membrane area. Let us imagine nothing has happened, everything is normal, and the area is also constant. And K is constant, we know that now. And H, thickness of your GI membrane, is also constant, let us imagine. So most of the constants are there, which you are converting them into a single constant called as P, called as permeability constant. We are trying to simplify this equation. Which equation? We are trying to simplify this Fick's first law of diffusion equation to understand the kinetic aspect. Hello? You can always ask me any doubt. I feel I'll be speaking to screen continuously. So to this equation is further simplified. See, to understand the what rate, what kinetic does the diffusion process happens, whether the first order kinetics or a zero order kinetics, we'll understand that. To get to know what kinetics the drug diffusion is happening, we are simplifying this equation now. This equation is further simplified, assuming them, converting means this DAK, we are assuming all this as a constant. Since all these are constant, we are just replacing that all the constant, that is constant, into one single constant, that is P. It is called as a permeability constant P. So now there's one more thing. Okay, forget about this pink color, whatever I have written here. Just look at the equation, how it is simplified. dq by dt is equal to P into CGI. Something is missing, you might feel, that is your CP. CP is also been removed here. If you look at that previous equation, whatever you have written, even that CP has been removed. So even this CP has been removed, So we are converting all this into a single constant and we are removing the Cp. And now your final equation is dq by dt is equal to P into Cgit. Let's see why the Cp has been removed. Why the Cp has been neglected. This is because of the condition called as a sink condition. So in simple term, let me tell you, when the drug absorbs from the GI fluid to the systemic circulation, based on the concentration gradient, it is happening. Drug comes from GI, it is coming to systemic circulation. The drug molecule will not stand there for a long time, right? The blood is in dynamic state. It is not a static. Static means not standing, idle. It is moving. The continuous flow of the blood is happening. So whatever the drug molecule come to the GI fluid, it is immediately carried by the blood to the next area. Means there is always a continuous concentration gradient and no chance for equilibrium to happen. If the equilibrium happens, then the absorption will stop, remember, because the major driving force, that's what we understood, is mainly the concentration gradient. If this concentration gradient is always at the higher side, you can imagine the continuous absorption happening. And that is what happens in our body because this plasma concentration is always at the lower side because the drug molecules is carried away by the blood because of its dynamic property. So it will not allow the drug to undergo equilibration. This equilibrium will not happen because of the dynamic state of the blood. Let us imagine if the blood is in static, it is just still, no movement. Then equilibration happens very fast and absorption will also come to halt. It will not further undergo absorption process, but that doesn't happen naturally in our body, that is inside our body. It's mainly because of a condition called as a sink condition. So remember this condition is what, where the continuous driving force is maintained in the bloodstream because of the dynamic state of the blood, and that condition is called as the sink condition. Since the Cp is negligible, the concentration of the drug in plasma is negligible, we are actually removing that Cp term in the equation, and finally the equation is simplified like this: dq by dt is equal to P into Cgi. And this is a typical first order equation, kinetic equation. So passive diffusion, which is explained by the fixed law of diffusion, based on that what we understood is it follows the first order kinetics. Hello. Fine. So you got understood what is sink condition? All are sleeping. Shama.
Yes, ma'am.
Okay. You understood what is sink condition?
Yes, ma'am.
Vidya.
Yes, ma'am.
Okay. It's nothing. It's simple. In simple language, the concentration in the plasma is never attained. I mean, we are not the blood flow doesn't allow the concentration of the plasma to attain equilibrium. So always the concentration gradient is maintained. So the drug molecule keep on moving from the GI lumen to the blood circulation. So ultimately, what we understood, the passive diffusion, the passive absorption process follows first order kinetics. So overall, to understand the important features of the passive diffusion, if you look at the slide, it's a downhill process. It's a downhill process. The reason the word downhill is used here is because the drug is moving from higher to lower concentration. That's why it is called as downhill process.